Welcome to Module 9. Module 9 is about regression, and for that, we start by finding the regression equation. So what is a regression equation? Well, given the collection of paired sample data, the regression line, or sometimes it's called the line of best fit or least squares line, it is a straight line that best fits the scatter plot of the data. So I'll show you how to create that line from the scatter plot. But the regression line is the equation that comes with that straight line. It comes from algebra. So I recommend if you didn't have a algebra class or it's been a long time since you have algebra class, I recommend you read the Module 9 PDF that I created. It's in the same place as this Excel file. So before you get going, if you're unsure about a little bit of an algebra background, I recommend you read the PDF. So from algebra, we know that regression line or the regression equation has a form of y hat is equal to b0 plus b1 times x. So b0 is the y-intercept, and b1, that's m in algebra, but here we use b1 to denote the slope. So the y hat is the predicted value. So what we use regression for is given the data, for a certain value of x, I want to make a predictive value of x. What a predictive value of y? What would that be if I put the value of x in? So we're going to use, so your task to figure out the b0, the intercept, and b1, and given the x, make the predicted prediction what the y hat should be. So here's a slope, here's a formula for slope and the y-intercept. We're going to be using Excel to figure those out, but in case you're curious, those are the equations, or those are the formulas there. So let's take a look at the example from last module about the shoe print lengths and the heights of males. So we want to use explanatory variable x, which is a shoe print length, to predict the value of y, which is the response variable, which will be the height. So here I have reproduced the table, and first thing I do is find the correlation coefficient, which we'll use in a little bit. So for the regression equation, I need to find two things, the slope and the y-intercept. So to use Excel, use the slope function, equal sign slope, and first choose the y values, comma, and the x values, close parentheses, press enter, and you get the slope. For the intercept, you use a function called the intercept, and you do the exact same thing I just did for the slope. And then for the intercept, I get a value of 125.41. And you combine the two, just say run it to 2 digits, you get the regression equation of y hat equal to 125 plus 1.73x. So once I know the x, I can plug that in and get the value y hat. Another way to get this regression equations from the scatter plot. So you'll be asked to recreate this kind of a scatter plot. So how do you do that? Well, select the table, go to insert, and then under charts you see all these dotted ones. Click on it and click the first one, and it creates a generic scatter plot. A couple of things you want to do: change the title, double click on it, and change it to scatter plot. Okay. Sometimes you want to add the axis label, like here. And there are two ways to do it, depending on the version of Excel. If you have Excel 2013, just double click on those numbers, and you see the plus sign here. So click on it and pick axis titles. And then also pick the trend line while you're at it. And then click out of there. And you have axis title, so double click on it. Erase it, and just say height, for example. I'll go down here, shoe print. If you have Excel 2010, it's a little bit different. Just click on the chart, and then on your Excel, you have chart tools. Go to that that chart tools tab, and then pick on the axis titles, and then pick both horizontal and vertical, and then these two will show up. And that's how you do it in 2010. So I have the labels, the title, and then the trend line. So I want to get this equation and then R square value. How do you do that? Double click on the trend line you just created and pick the linear as your choice, and scroll down and click on the display equation on the chart and then R square value on the chart. We'll use the R square a little bit later, but for now let's look at the equation. When you look at the equation, you see that it's the regression equation, same as what we just found. So either way, you can find the regression equation from the chart, or you can simply calculate it yourself. Either way is okay. And this is how you create the R square value, which you'll be using a little bit later on. Okay. So back to the original scatter plot. So let's make predictions. First thing you have to do is determine if the regression equation is a good model or not. Is it a good model or a bad model? So the key factor is the regression equation is a good model, meaning that you know that if there's significant linear correlation, which you learned in the last module, if that's the case, you use the y hat value. So y hat, that's same as a predictive value, to find the predictive value y. If you find the regression equation is not a good model, which means that there's no linear correlation, so you find that there's no linear correlation, that means the equation is not a good model. So then instead of using y hat, you use the y bar, which is the same as the mean value of y. So let's continue with the example and see what happens. So we had the 5 pairs of shoe print lengths and heights to predict the height of a person with the shoe print of length of 29 centimeters. So given that shoe print length of 29 centimeters, I want to predict the height of the person. So let's look at first the correlation coefficient, which we calculated earlier, 0.59127. And you compare that with the critical values of R, which is in the tab right here. Go to there. And look at the values for when n is 5. These two. So 0.878 and 0.959. If you go back to the regression tab and compare those numbers with a correlation coefficient of 0.591, you see that even at alpha 0.05 or 0.01, 0.591 is less than 0.878 or 0.959. So that means there's no linear correlation. So that means we concluded the regression equation not a good model. So because the regression or correlation coefficient is less than those two critical values, we determined that the regression equation that we just figured it out is not a good model. So in that case, we'll be using the y bar, which is the average of y values. So here, I just took the average of these numbers. So that's the case of when regression model is not a regression is not a good model. Just take the average of the y values, all of them. Okay. So here's a tip: if you do determine the regression equation is good, then you can either use a forecast to make a single prediction or trend function to make multiple predictions. That's just an FYI. So let's move on to examples 3 when another set of data sets. So scatter plot and the regression equation are shown for 40 pairs of shoe print length and heights. Again, make the prediction for the height of a person whose shoe print length is 29 centimeters. Now let's say that we already know the correlation coefficient to be 0.813. So later on, we'll figure out how to get this equation here. But for now, let's take this as given. Y hat is equal to 80.9 plus 3.22x, and the correlation coefficient is 0.813. Is this a good model? Yes or no? So let's figure that out. So in this case, n is 40. So we look at here, 0.312 and then 0.402. You see that the correlation coefficient is bigger than either value. So that means this regression equation is a good model. So then we plug in the 29 into x to figure out the y hat. So how do we do that? Here's 29. Equation is 80.9 plus 3.22 times x. So for this, you can do a manual calculation or just use Excel. 80.9 plus 3.22 times C109, which is 29. So in this case, my y hat is 174.28. Now let's move on to the prediction interval here. So prediction interval is an interval estimate of a predicted value of y. So you've seen something similar before. The interval estimates of parameters are considered to be confidence intervals, but the interval estimates of variables, in this case the y, they're called the prediction intervals. So just like the confidence intervals, we have a formula for margin of error, prediction interval notation, and another thing called the standard error of estimate, which is it's part of the margin of error calculation. So let's take a look at all these formulas. So if we use the 40 pairs of shoe lengths and heights, construct a 95% prediction interval for the height, given that the shoe print length is 29 centimeters. So the data is given in the foot tab. So we'll take a look in a little bit. But we need all these values. So we need the y of 0, x of 0, which is given 29. We're going to need the s of e, the standard error. We're going to need the y hat, confidence level, and degrees of freedom, and t. We need all these things in order to calculate the margin of error, which the formula is here. This is one of the craziest formula you will see. But we'll use Excel to figure out the margin of error. So if you're asked to find the prediction interval, you need to do all these calculations. So let's look at the foot tab. So we've seen what we need for the prediction interval. So B0, B1, the slope, and then intercept. We're given the x of 0. So we need to figure out the y. And then we know what n is. And we're going to figure out the standard error. So for the intercept, again, I just used intercept function, intercept. And then clicked on all the value of y first, these values. So just select all the data in that column, and then comma, and shoe print. Okay. I did the same for the slope, except I use the slope function. I know what the 29 is. So make the prediction here using the formula. This formula, I'm going to multiply the slope by x and then add the intercept. And that's what I did. Intercept plus slope multiplied by the x given. So confidence level is 0.9, n is 40, and I need to figure out standard error. And then to do so, you can do it two ways. Follow the formula or use Excel to figure that out. So I'm going to do that right now. To do so, go to the Data tab and Data Analysis. If you don't have it, go back to the first tab and then install this data analysis toolkit. Go to there and pick regression. Press OK. And then you ask for the input Y range, which is the height in this case. So select all those numbers. And then for the input X range, select the shoe prints. Okay. Gotta redo it one more time. Make sure to include the label, the shoe print, in this case. And if you did include the labels, click on the labels, and then select the new worksheet for the output option and press OK. I'm not going to do that because I already created the table. So that's what the output table looks like. When you look at it, you see the standard error of 5.943761329. That's your standard error. So you can use that as your standard error. I did figure out the standard error manually down here, so you can see they're a match. So you can use either one. So going back to the prediction interval, I reference the output B7, which was here. So equal sign, go to the output tab, click on B7, enter, and then that carries over here. So I know the Y hat, confidence level, and degrees of freedom. Let's figure out the T first. So it's the same as before. We'll use the two-tail function. So here it is. So in order to calculate the margin of error, a few things you need. You need the T value, which we just got. We need a standard error value, which we calculated up here. We need N, which is right here. X of 0, which is 29. X of bar, which we'll calculate. So we need X of bar, sum of X squared, and then summation of X squared. So I need these three things, which I already did in the foot tab. So let's go there. So to calculate the average X bar, you just use the average function, just like before. To get the summation, use the sum function, just like before. And then you will need to create another column, maybe label it x2 or x squared, where each value is a square of x. So equal sign, click here, caret 2, enter, and then just drag it down. And you get the values of x squared. And at the bottom, just sum it all. So that's how you get x bar, summation of x, and then summation of x squared. Going back to the predicted value, those are the things I needed. So again, I reference for x bar D44 here. Sum of x, which is down here. And then sum of x squared is down here. Okay. So once you get these values correctly, and then you copy and paste the formulas in these cells, this cell reproduces this whole thing. So once you get the margin of error, the rest is the same. The lower end will be y hat minus this number, and the upper end will be y hat plus this number, as you can see down here. The conclusion is that this means that we are 95% confident that the interval 162.1 to 186.5 contains the height of 174.3 centimeters when the shoe print length measures 29 centimeters. So just a quick recap. Finding the margin of error is very tedious. You got to make sure the X bar is correct, this is correct, this is correct, and then you can do so in a different tab, which I recommend, and then just refer back to the original tab. So make sure you understand how to figure out the margin of error confidence interval for your homework and the quiz. If you have any questions, let me know and I'll try to help you out. Okay, so let's move on to variation. So earlier you saw the value of r squared. That is just the ratio of explained variation divided by total variation. So Excel can produce the r squared value. This is just a reproduction of the output we just created earlier. So it's right here. So when you see r squared of 0.66, that means we concluded that 66.1% of the total variation in height can be explained by shoe print length, and the other 33.9% cannot be explained by the shoe print length. So there's a relationship between the explained variation, unexplained variation, and total variation, which is seen in this formula here. So to get the total variation, first you need to figure out the explained variation and an unexplained variation and add them together. So how do you do that in Excel? Here's an example. Consumer Price Index, CPI, and the cost of a slice of pizza in New York are listed below. Find the explained variation, unexplained variation, and total variation. So here, I did it manually, so these numbers are what's given. And from there, I calculate the explained variation and then unexplained variation. And this is just a sum of these two numbers. So how do you reproduce this using Excel? Here's how. Again, go back to the Data tab, click on Data Analysis, a regression, OK. Input Y range here, input X range here, labels, okay, and it produces this. And then the variation, explained variation, unexplained variation, and total variation are under the headline of SS. So 2.648 is the explained variation, 0.8 is unexplained, and 2.728 is the total variation. So let's go back to the variation tab. You see that the 2.648 is explained, 0.08 is unexplained, and then 2.72 is a total. So that's how you figure out the variations if you're asked. Just FYI, on your output, these won't be highlighted. I just colored these just to show where the numbers are. Okay. So R square is pretty high, so it's most likely the variation is explained by the explained variation. One thing you'll be asked to do is add a data point. So let's insert a data point here. Say 200 and 200. And see if that data point's either influential, outlier, either or neither. So let's figure that out. To see if the added data point is an outlier or not, easiest thing is to plot it. So let's plot this. Insert, scatter plot. And it looks like at 200 it's way over here, and then everybody else is down there. So this can be considered to be an outlier. So easiest way to figure out if some added data points, whether it's an outlier or not, just plot it. And if it's way out there, it's a little subjective, but in this case, it's very clear that added point is an outlier. Okay. Is it influential? To do so, do the regression analysis to include that point. So data analysis, regression, and for the input range, select the Y, including the added one, and then X range, same thing, labels, and create another worksheet. Let's change the length. So a few things. This is the variable correlation. So let's see if there's any if there's a linear correlation or not. So observation 7. So let's go back to the critical value of R. And I see it's 0.754 and then 0.87 or 0.875, which is bigger than this. So that means there's no linear correlation. Looking at the R squared, if you compare this to the original one, 0.97, 0.166, you see the dramatic difference between the two. So that means that roughly 16.6% of total variation can be explained by the CPI. So that means this newly added point is influential, yes, but it's an outlier. And it does dramatically affect the conclusion of the regression analysis. So if I were doing this analysis, I would take this point out and then stick with the original 6. So that's the conclusion of module